Okay, here's an example. Find out how many positives and how many negative real zeros there are for this function. Well, for the positives, there's one sign change right there from positive to negative. There's a second sign change and a third sign change. So there are three or there are one positive real zeros. So if I start looking at the positives, I'll definitely find one. For the negative x part, it goes negative x to the fourth minus 3 times negative x to the third minus 34 times negative x squared plus 108 times negative x minus 72. I'm going to simplify that. I get x to the fourth. That negative becomes positive. This stays negative, but it changes the sign of this, so it goes plus 3x to the third. This one becomes positive, but there's a negative in front, so it's minus 34x squared. This one changes to minus 108x, and this stays negative 72. So now counting the sign changes for f of negative x, there is only one, so there's one negative real zero. So if I've got my list of p's over q's and I'm going to start looking, I think I'm going to look at the the positives first, because there could be three of them and they might be easier to find. There's definitely a negative one and a positive one for me to find out there. So maybe start with the positives because there might be three and it might save me some time. Okay, that's the Descartes rule of signs. Gives you a little hint as to what p over q values you could start looking for. Now, rule number 2, I think, is better. The upper and lower bound theorem. Okay, this is going to sound very complicated, but once you go through it once or twice, it's going to make a lot of sense to you. If x minus c and synthetic division for a polynomial, the following are true. If c is greater than 0, so I'm trying a positive 0, right? And each coefficient in the depressed polynomial, when I'm done with my synthetic division, the numbers at the bottom, if each one is positive or 0, we can think of a 0 as a placeholder in this upper bound and lower bound theorem. C is an upper bound. Now, how's that helpful? That means there is not a 0 larger than C. Not a 0 larger than C. So if let's say I'm putting a 4 in for synthetic division. I put a 4 in and I go through and I do the division and I don't get a 0, but I do get a bunch of positives down in the bottom. What that means is I know I don't need to try anything bigger than 4 because 4 is a upper bound. There won't be an x-intercept bigger than 4. So when you have your list of p over q's, start in the middle. If you don't find an answer but you do find it's a lower bound, you just cross off the upper half of your numbers. If c is less than 0, and each coefficient in the depressed polynomial, this one's different than you think, so pay attention here. If it alternates from positive to negative as you go through those coefficients in the bottom of the synthetic division. If it goes from positive to negative, 0 can be a placeholder for either one of them. C is a lower bound. That means there is not a 0 smaller than C. So what do I mean by this? If I put negative 5 in for synthetic division, I go through my synthetic division, I don't get a 0, but the numbers underneath alternate, negative, positive, 0, positive. If 0 can be a placeholder, then I know that negative 5 is a lower bound. So I can cross off numbers lower than that. Okay, here we go. List all of the possible rational zeros for this particular x to the fourth function. Now it's a 12 there, so the factors of 12 are 1, 2, 3, 4, 6, and 12. That's going to be a negative 12, negative 6, negative 4, negative 3, negative 2, negative 1, 1, 2, 3, 4, 6, and 12. That's a lot of potential zeros. We could have a maximum of 4 of them that we find. How many positive and how many negative real zeros should we be looking for? Let's see if Descartes' rule of signs can help us look where we should be looking first. For the positives, positive, positive, negative, there's a sign change. Negative, negative, positive, there's a second sign change. So for the positives, we could find 2 of them, or we could find none of them. Again, I'll explain why we subtract, why it could be both options. I'll explain that at a later time. It will make sense. For the negatives, I've got to find f of negative x. So I put negative x in here. I got negative x to the fourth plus 2 times negative x to the third minus 7 times negative x squared minus 8 times negative x plus 12. Okay, that's going to turn positive, so x to the fourth. This will stay negative, so negative 2x to the third. That turns positive, but there's a negative in front, so negative 7x squared. This turns to positive 8x and plus 12. Okay, we got some sign changes. This one's positive and that one's negative, so there's sign change number 1. It stays negative, we get back to positive, there's sign change number 2, and it stays positive. This is also 2 or 0. So in this scenario, Descartes' rule of signs didn't even help us at all. Both of them could have 2 or 0, so it didn't help me either eliminate one of them or have one that seems more likely. So we're just going to have to guess. Now here's the thing. I want to use this upper and lower bound theorem. So I'll show you what. I'm gonna guess 12. All right. Don't write this in your notes because let me flip the page here in a second. Oh, there it is. We're going to start looking for upper and lower bounds and stuff. So I just want you to see something. Okay. I seriously doubt that 12 is one of these zeros. So I'm going to put 12 in just so you see. There's a 1 for x to the fourth, a 2 for x to the third, a negative 7 for x squared, a negative 8, and then a 12. I got a hole in the paper there, so I had to write it kind of funny. Bring down the 1, multiply, and I get a 12. Add this, I get 14. 12 times 14, I got to go to La Calculadora for that. 12 times 14, oops, I screwed that. That's okay. That's 168. And then I'm going to subtract 7, so I'm even going to do that on the calculator, 161. Well, now I got 12 times 161 is going to be a big fat 1,932. Then I subtract 8. That's 1924. Now I'm going to multiply that by 12, and here we go with a big giant number, 23,088. And when I add 12, I'm just going to miss 0. It's almost a 0. It's 23,100. Okay, that's clearly nowhere near being an x-intercept. But look at these values. Positive, 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 positive. What that tells me is 12 is an upper bound. There is no way there is any x-intercepts bigger than 12. I mean, we had a list of them here anyway, but this didn't list the irrational numbers. So it still could be square root type numbers, but it's definitely not going to be bigger than 12. There is no possible real number bigger than 12. That's an x-intercept. Okay, that's how the upper bound theorem works. Let's go to the next page.